Hello everyone, I am Cristian Fabián Sotile. I'm a PhD student from Universidad de Buenos Aires, and I will be presenting Polymorphic System I, which is a joint work with Alejandro Díaz Caro and Pablo Martínez López. Let me start by saying what this work actually is about, and it is about identifying isomorphisms between types, which translates into abstracting out details of usage of the terms that allows us to do the same things or get the same results from, which is what actually isomorphisms capture, right? We will see this in detail now. So this presentation is going to start with some introduction and motivation of the subject. Then I will be talking about the state of the art, and then I will properly introduce polymorphic system I. So what type isomorphisms actually are? We say two types A and B are isomorphic if and only if there exist two functions f and g, such that f is a function from a to b and g is a function from b to a, and composing g and f is the identity on a, and composing f and g is the identity on b. And this means that for any term t of type A, there exists a t prime in B such that I can transform t into t prime using f, and then I can get t back from t prime using g. And this, of course, happens vice versa from B to A and from A to B again. And this translates into we can get the same results from this t and this t prime. We will explore this now. I'll give some intuition and examples about this. So I said isomorphisms capture the utility of types, what we can do with them, what we can get from them. So let's take, for example, the commutativity of the product. We have the types A product B and B product A. We have these terms C and G prime, which are of those types. And we know we can get an A from T projecting the first element, and we can get the same A from T prime by projecting the second element. The same happens with B. And this occurs because these T and T prime are those that are isomorphic, right? T transforms into T prime with F, and T prime transforms into T with G. And within the carry isomorphism, we have T, which is an uncarried function. We have T prime, which is a carried function. And we know that applying T with a pair gives us a C, and applying T prime with two separate elements gives us a C2. The distributivity of the arrow with respect to the product isomorphism, which is probably a less known isomorphism, say that T is a function from A to a pair B and C, and T prime is a pair of two functions A and B and A to B and A to C, and we can apply T and then project, and we get the B, and we can project T prime and then apply it, and we also get the B. The same happens for C. But there are also some intermediate combinations, right? Not eliminating all of the constructors in the term. Like, for example, this T prime getting applied with just one argument that gives out a function from B to C. This T being applied with just being applied and not projected, which results in a pair, and this T prime being projected, short resulting in a function, and we will see that these intermediate results are interesting for our purposes. And it was clear from here that we actually are able to get the same results from these isomorphic terms. So, some past work on type isomorphisms. Ritri worked on a library to search functions in the library by types, by considering types up to isomorphisms. Um, there, there's been a characterization of every type isomorphisms which is within different systems, such as lambda calculus with pairs, System F by Di Cosmo in mid-90s, and also a software for searching lemmas in a Coq library by types, considering types up to isomorphism too. So this effort towards searching functions, searching lemmas in a library are about taking advantage of the software already written, because if it is easier to write a software than to search for it, well, maybe it's going to be rewritten too many times. So what is our proposal? We want to study the consequences of language where isomorphic types are identified. This means that given two types that are isomorphic and given two terms of the same type, these two terms that also are isomorphic, we want to allow to use T prime where T would be traditionally used, right? We will see an example soon. And this expands the legal term combination for T to all those of T prime, right? So, for example, let's take the carry again. We have in black the previous examples, and in red we have what we want to be able to do, right? We want to be able to this function t, which expects a pair. We want to pass it two separate elements, and we want to pass to t prime, which expects two separate elements, this pair of elements. And we want to also apply t with one argument, right? This is a pair of two elements. I want to give it just one element. And about the distributivity of the R with respect to the product, we want the same, right? We have this function that needs to be applied first and then projected, and we want to be able to project it and then apply it, and of course we want to be able to just project it, and in this case, which we should first project, we want to be able to apply. And we know this is safe because of the type isomorphism, because we know how to transform, for example, this term into this term. And the idea is to abstract out the details of usage of these terms, because we say that, okay, we can get the same, we can do the same with them, we can get the same from them, and the only difference is how we combine it with some environment to get the same results. So the proposal is to allow all these combinations to happen, and the system will make this work. So now I'm going to introduce System I, which is a work by Diaz-Caro and the WEC. It is a simply typed lambda calculus with pairs, where all the isomorphisms from the fragment of the arrow and the product are identified. So this means that there's an equivalence on types, and these types are considered the same, right? This type, the commutativity, carry, distributivity, are considered the same type, and they added a typing rule which says that if two types are isomorphic, then if we have a term of one of the types, then it also has the other one of the types. And now we can type, for example, this term, which is an abstraction expecting an A and then a B, and we're giving it a B and then an A. Of course, this is not typable in traditional systems, but here it is because we have carry, we have commutativity, and we have carry again. But then we can see that beta reduction gets broken. So what we do is we add an equivalence on terms, right? I'm sorry. This is broken because this should be substituted by an A, and it is actually being substituted by a B. So they added an equivalence on terms, right? So this pair is the same as this other pair, which is the same pair just swapped. An application of function with the pair is the same as an application of that function with the two elements of the pair separately. And an abstraction that gives us a result a pair is the same as a pair of functions where the first function computes the first element of the pair and the second one computes the second element of the pair. And they also restricted the beta reduction, so this can only reduce if the argument has the same type as the variable being abstracted. So let's see an example. Under these circumstances, this term that was bad formed because now that we restricted beta, this term is actually, if we don't think about this, it is stuck. But now that we are considering these equivalence on terms, this term via the curry equivalence gets transformed into this other, right? Because we have two arguments, we have a pair here. This pair now can be swapped by the commutativity equivalence into this other pair, and this whole term can be transformed by the curry equivalence again into this term, which is what we are used to see, and this is okay, and this can be this is fine. So let's talk about the pairs. What happens with pairs here? Well, since we have this equivalence on terms, this swapping equivalence on pairs, the naive approach for projecting a pair doesn't work because we can project this pair and we get an R, and we can project this other pair and we can transform it through the commutative equivalence into this other projection, right? And then we are getting an S, and well, if R and S has different types, this is wrong. And so the new rule will be to project with respect to the type. So if R has type A, then I will say that projecting the A from this pair gets me an R. So what happens with this is that if the two terms have the same type, this behaves non-deterministically, but that's fine. That's not the problem, because okay, so it behaves non-deterministically. Sorry, because projecting the A from here gives an R because R has type A, and it also gives an S because S has type A, right? But this is fine because pairs just have a different semantic when isomorphisms are identified. So when we are in the process of this commutativity isomorphisms for the product, the pairs are non-deterministic. From the logic perspective, it is a way of proof irrelevance. And from the programming perspective, we can encode determinism when we need it. For example, adding dummy abstractions for the elements we want to project, and then, of course, providing B and C are different, right? And then projecting using the type we chose for the encoding. So let's see some previous results about System I, regarding System I. There's been an implementation of System I by Diaz-Caro and Martinez Lopez in IFL 15, where they added a fixed point operator to have recursion. They added natural numbers. They added mutual recursion, and they directed the rules for term equivalence. So they have rewriting rules now, and they added some rewriting rules to have progress. For example, this partial beta that allows for one of the things I said we wanted, that was to have an abstraction on pairs and give it just one argument of those of the pair. And this delayed beta that allows us to apply a function that expects two arguments, passing directly the second argument, like jumping over the first abstraction, and this makes sense. And then they realized that, well, first, there's no progress in System I because this term is stuck, right? And they realized that the results achieved with delayed beta can also be achieved with eta expansion, because this term can get transformed into this other term, right? Added abstraction, duplication. And we know, this is the previous example we saw, that this term can just swap its arguments and transform into this. And this better reduces to exactly this term, which was the one that delayed beta gave us. This is this is a work that is now under review. But well, now this, using this, there's progress in System I. There's progress in System I. And G and type distributed lambda calculus, which is a work by Agatoli and Diaz-Caro. We know that lambda calculus with pairs has clashes, right? Because we have this introduction of the product, and we are trying to eliminate an arrow, and we have this introduction of the arrow, and we are trying to eliminate the product. And these are terms that are stuck, and they are eliminations. So the system as it is has no progress. But if we take these term equivalences, right, these two as rewrite rules for this lambda calculus, we get that this elimination gets transformed into an introduction, and this other also into an introduction, and we have that all normal forms are introductions. So we have progress in this calculus, since these terms are no longer stuck. So so the interesting thing here is that in the M-type lambda calculus with parent, there's progress. So let's see some relevant consequences about these works. We have a sort of enhanced partial application. This eta expansion gives us that, because we are able to do this and to pass the argument we want, not taking into account which is the one that it's actually expecting the function, right? So the functions can be applied with the arguments we have at hand right now, and there's no need to manually flip the function to make it match the current argument we are trying to apply. So for example, we will be able to apply lm, right, the Haskell function, giving it an element, and we're able to apply lm giving it a list, and this makes sense, and these are two different functions, right? lmx is different to lmxs, and we can also apply, of course, well, taking into account the previous example of swapping arguments, we can pass to fold L the arguments in any order, and in particular, we can define this function mm, with the arguments, with the parameters defined in any order, right? And this is something I would be grateful, because I tend to forget which is the correct order for the faultel function. The this function, right? Not this. So another relevant consequence: we can discard code through function projection. So how we do this? Let's say we have this function, which is an abstraction that gives a pair as a result. We are projecting a function from it. We are projecting the function that goes from A to B from it. So we don't care about the C, right? This, of course, has type A to B. And through the distributivity equivalence, this is transformed into the projection of this pair of functions, and then of course I can get via the projection rule this function. So we can see that we have abstracted the function before it was applied. What we are used to is to, let's say we have this function, we have to apply the function, compute the complete pair, and then we choose which is the element we care about. And now we are projecting the function without computing the pair, right? So the subterm S, which is the one that here is the one that we do not care about, is actually discarded at not computed at all. So let's see, for instance, this example, this function div_mod, which computes a pair with the division between these two numbers and the remainder between the division of these two numbers, right? So it is defined recursively. We are assuming a more complex context where we have recursion, we have natural numbers, we have some syntax sugar for deterministic projection, well, I will use it first then. And so this gives a pair as a result, right? We can see that a pair is being computed, and we can extract, or we can compute using this div_mod function the integer division by projecting the first element, projecting the first notch, the first number from it, because when we do this through reduction, this function, in particular this div_mod_rect function, gets transformed into this function, where the parts that computed the abstraction were modified, right? Here we just have the 0, and here we don't apply anymore this function, because this is actually a number, right? So we modified the code, we optimized this div_mod function, and we extracted a new function, which was the one we were interested in. So now I'll be telling you about polymorphic system I, which is an extension of system I to polymorphism. Why we do this? It is the natural evolution of the system. The isomorphisms has already been characterized. The isomorphism related to the fragment with for all, arrow, and product. And it enhanced the expressiveness of the language. So the equivalence on types of system I gets extended by adding these two equivalents, these two isomorphisms, that says that the for all and the arrow are commutative, right? Of course, if x is not free in A, right? And we also say that the for all distributes over the product, which is kind of similar to the arrow situation, right? The distributivity of the arrow with respect to the product. And this, of course, induces some equivalence on terms. And these are just two examples, but there are actually more equivalences. For example, if we have an abstraction that is being applied with the type, then it means that the abstraction of the type is actually here. So we can jump over this abstraction and we can directly apply the type application within the value of the function. And this acts the same as the distributivity of the type of the arrow with respect to the product. Sorry. And by saying if we have an abstraction on types that has a pair as its body, it's the same as having a pair of type abstractions with the first element as the value of the first type abstraction and the second element as the value of the second abstraction. And we proved substrate reduction, which was not a trivial proof because of the it's not a trivial proof because of the amount of type equivalences that arise from this axiomatic type equivalences, right? But because this is actually a congruent relation on types. And it required a canonical characterization of types to be able to see which were the form of types that were actually equivalent. And we are currently proving strong normalization, which is a non-standard proof because we don't have neutral terms here, right? This term is an elimination and therefore a neutral term. And via equivalence, it can be transformed into this introduction, which is not a neutral term. And the classical Tate's proof relies on these neutral terms to prove its property CR3 of these candidates of reducibility. So there's a strong normalization proof for system I, which is particular, and we are trying to adapt these proofs to polymorphic system I, and we claim we will be able to have this proof by the final version of the paper. And the future work is to prove progress. As in system I, we plan to prove it by adding the add expansion rule and to add some constructors. We plan to add units, the top, maybe the bottom. And we plan to implement polymorphic system I. It hasn't been defined how or where this implementation will happen. It may be like systemized implementation, which is in Haskell. It may be as an extension of a basic subset of Haskell, or maybe as a library or core extension for theorem provers such as Agda or Coq. So that's all. Thank you very much.